Okay, today's first big topic today is going to be the chain rule in multi-dimensions, which sounds like it could be a little bit scary. So let's remind ourselves. In Calc 1, if I said y equals f of g of x, a composition of functions. Now, I could have f of g, of h, of q. You can go as many as you want. But the idea is, if I wanted to differentiate with respect to x, then dy dx was f prime of, now f doesn't see x, f only sees g. So it's f prime of g of x. Now I go inside and now I say, times g prime of x. So one of the first rules we remember from the chain rule in Calc 1 is that the argument cannot change, but this additional term here, sometimes you remember the chain rule factor. And it's a factor, it's not added, it's always multiplied. There's no exponents, it's just that. So if I wanted to do something like, let's keep it simple, I have the sine of x cubed. So that's a composition of functions. My outer function is the sine function, my inner function is the x cubed. So if I'm doing dy dx, think of these like doors. I have to open one door at a time, and all I see is the very first thing in front of me. So I only see the sine function. So then my thing is the cosine of x cubed. Again, that argument cannot change. And then my chain rule factor, of course, would be the derivative of the x cubed. So my answer would be 3x squared cos x cubed. And we're all probably pretty good at that because you can also integrate. Everything's wonderful. When you're using the chain rule in Calc 1, it's because you have a composition of functions. Regardless how many layers there are, I basically differentiate till I get to the inside. So now the question is, what happens when we have multiple variables? Particularly multiple independent or multiple dependent, okay, because we can do both. So let's consider a situation, excuse me. So let's consider a situation, how about, where I have z is a function of x and y, okay? But x and y are both functions of t. Now, we've actually done things like this when we had our vector valued functions. We had x, y's, and z's, but they were all functions of t. So right now, x and y are not independent variables. T is the only independent variable in this problem. X and y are not. So the question is, how do I take a derivative? Well, I can take the derivative of z with respect to t, but it feels like there's two different ways I can get there. So if I can get there two ways, first of all, is it dz dt or is it dz dt? And it absolutely matters. This is not arbitrary or random. So remember what the notation means. The stiff d's means ordinary derivative. Ordinary derivative means exactly one independent variable. Squiggly d's, that means partial derivative. That means more than one independent variable. You either have one independent variable or you have more than one. There's not a third option. Since ultimately t is the only independent variable in the problem, I'm actually asking this question. So there is no partial of z with respect to t. Now, z, how do I get to t? So I'm going to draw you a little picture that will really help. C sees x and z sees y, but x and y both only see t. I want to get dz dt, but there feels like there's two different routes I can take to get there. So I can go this route, or I can go this route. Now, this route would mean I'm differentiating z with respect to x, and then multiplying x with respect to t. And then I'm going to add to that z with respect to y, and then yt. Now, dx dt and dy dt are both ordinary derivatives because each one of these are functions of one variable. So the question is, ordinary or partial? Ooh, anybody want to try that one? The dz dx, is that an ordinary derivative or a partial derivative? Look at my picture. What do you think? Just yell it out. Ordinary or partial? I couldn't hear. What's it?
Partial?
Partial. because Z sees two different variables. Z doesn't see T. Remember the chain rule, you always go for the next variable. You keep going. Z only sees X and Y. So I can take the derivative of Z with respect to X or with respect to Y. So these are both partial derivatives. Now that's a little confusing, but actually it's because I have choices. If there's more than one, it's going to be partial. If there's only one, it's going to be right, an ordinary derivative. So let's do a simple example of that. Let's suppose that Z equals, I'll keep it real simple, X cubed Y squared. But X equals, how about e to the T and Y equals sine T. Okay, so then technically dz dt, the partial with respect to X would be 3x squared Y squared, then dx dt, that'd be e to the T. Plus, now I can do the Y, so that would be 2x cubed Y, and then cosine of T. Now, we have a problem right here. I have too many variables. So what I would do at this point is I'd insert these guys. So this should be 3 e to the T squared sine squared T times e to the T. I wrote that correctly, plus 2 e to the T cubed times sine T times cos T. So finally, it looks like, if I clean this up, 3e to the 3t sine squared T over here plus 2e to the 3t sine T cos T. Now, obviously, I can factor that. In fact, I probably should factor that. But if I walked away right now, that's the best answer I can give. Now, could I have put these guys into here first? Yes. And that would actually make this a much shorter problem. But I wanted to do it the long way to confirm that we're going to get the same answer. So let's take the same problem. Let me insert these guys into here. So then Z equals e to the 2t sine cubed T. So dz dt, now this is a calc 1 derivative. First times the derivative of the second. And there's my chain rule at work right there. Plus the second times the derivative of the first. Now look at that answer right there. Do I have all the same stuff here? Did I lose? Hold on a second. Feels like I lost something somewhere. So we got first times the derivative of the second. Second times the derivative of the first. I think I lost a sign somewhere. Hold on. Did anybody see it? Oh, hold the phone. So I see the same terms, but somehow I see them in the same order. E to the, oh, no, we got it right. That's e to the.
The powers are off.
That should have, I got it backwards, didn't I? Ah. Yeah, I'm looking at that going, that doesn't look like the same answer to me. That should have been 3t and that should have been sine squared. There we go. That'll make it a lot better. Okay. So this should be 2 sine, okay. And then this one was 3, 2, there we go. Boy, that would have been a disaster. And that's times 3, there we go. So that one right there looks like that one right there. And then that one right there looks like that one right there. The fact that I got the same answer just means, okay, that did the chain rule correctly. Most of the time, and you know this from Calc 1, if you had the product of 2 polynomials, you could use product rule, or you could just multiply the polynomials first and then differentiate that. That's probably easier most of the time. If I can manipulate something first, it shouldn't change my answer, but we just want to go the correctness of how to take a derivative. Now that's the first case. There are a few different cases. So that's the case where I had a function of more than one variable, but each variable ultimately was a function of the same thing. Okay, again, that's case number 1. Case number 2, let's look at the situation where, excuse me, y equals f of x, but x is going to be a function of, let's say, r and theta or something like that. Okay. Y is a function of x, but x is maybe polar-ish. So now I've got, okay, y only sees x, but x sees r and theta. So there's two different derivatives I can take. I can take the derivative of y with respect to r. I can take the derivative of y with respect to theta. So I've got the derivative of y with respect to r. I've got the derivative of y with respect to theta. Would these both be ordinary or would they both be partial? Well, right now, r and theta are both independent variables. So I want to take the derivative of y with respect to this one or with respect to this one that can only be partial. Now, oops, one more. How do I get to here? Well, I got to go through x and then this way. But the derivative of y with respect to x would be ordinary because y only sees the one variable. So this would be dy dx. But then x sees two variables. So the partial of x with respect to r. Then this would be dy dx, the partial of x with respect to theta. So actually that wasn't all that terrible. So in this case here, again, the ordinary derivative, because this only saw the one variable, this sees multiple. Okay, now there's one more case, and that's probably the worst one. That's where I have a function of more than one variable. Let me erase this. Let's say z is f of x and y. And I'll use polar again because that seems to make sense. And then x is g of r and theta. Y is h of r and theta. So z sees two variables, but so do x and y. So ultimately, z is a function of both r and theta, ultimately. So whatever these were, I could substitute them back into here, but still there are two independent variables, r and theta. I can take the derivative of z with respect to r, or I can take z with respect to r, or I can take the derivative of z with respect to theta. Both are correct. Okay, but those are the only two that I can ultimately take. They're both partials because, again, ultimately I have two independent variables. Now, to get there, this r is not the same as this r. This is the r in this function. This is the r in this function. So if I want the partial of z with respect to r, notice I can take this route or I can take this route. So I'm going to add them like we did in the first example. So this would be the partial of z with respect to x times the partial of x with respect to r plus the partial of z with respect to y, the partial of y with respect to r. There are two different ways to get to the r, so I add them. Here, partial of z with respect to x, partial of x with respect to theta. Partial of z with respect to y, partial of y with respect to theta. I always like drawing the picture here, the little flow chart, if you will, because now it doesn't matter how many variables I have. It's very easy to analyze and decide, is it a partial derivative? Is it an ordinary derivative? I have to multiply because this is the chain rule. I'm taking the derivative of this guy and then following it with the chain rule factor in a sense. So both of these are chain rule factors. Okay. Now that seems very abstract. It's actually very, very simple to apply. And as a result, it's going to give us a tremendous shortcut that we're going to do momentarily. Now in Calc 1, if you ask any student, what is the most hated form of differentiation? I think we went over this before. Anybody know the answer to that?
Implicit.
Implicit. Oh God, it's just evil. It's like, you know, again, is that guy that got picked last in kickball every day in recess, and this was his way of getting back to people. Women are just not that mean. Men are that mean. They go, I'm going to come up with something that nobody likes, but everybody has to do it. Implicit. Well, it turns out implicit is the only way to get answers in some cases, and it can be kind of nasty. So I want to remind you, what does it look like? Well, first of all, implicit means I cannot solve explicitly for the dependent variable. So something like this. Excuse me. I've got maybe x cubed y squared minus the cosine of xy, and that's equal to, I don't know, e to the xy squared. I think that's sufficiently evil. And I want to find dy dx. Now, it's not possible to isolate the y. I can't write y equals function of x. That's not too many y's. They're inside things. But whatever this is, I mean, this might be some really weird figure eight. I have no idea what that looks like. I can still ask what's the slope of a tangent line at any point on the graph. And that's just a derivative. But in order to take the derivative, we had to do it implicitly. So what we do is we take the derivative of both sides with respect to x. Why with respect to x? Because I want dy dx. This statement right here implies that y is a function of x. Y is the dependent variable, x is the independent variable. You can't read it any other way. So think of this, and the way I do it in Calc 1, I usually introduce it like x cubed f of x quantity squared. It's function squared, not variable squared. So first, times the derivative of the second, which would be 2y to the first times the derivative of y, plus the second times the derivative of the first. Yikes. The derivative of negative cosine would be plus the sine of xy times the derivative of xy. Oh, that would be product rule. First times the derivative of the second plus the second times the derivative of the first. That's just my left side. Equals. The derivative of e to the thing is e to the thing times the derivative of the thing. Again, product rule. First times the derivative of the second plus the second times the derivative of the first. Oy vey. Now, I'm done with the calculus. Now what I need to do is gather the dy dx terms. So I need all the dy dx terms on the same side, but before I can do that, I have to distribute here. I have to distribute here. No way around that. So let's rewrite this. This is now 2x cubed y dy dx plus 3x squared y squared. You don't have to rearrange the x and y, but the coefficients do have to come in front. The definition of a coefficient, it's the multiplier in front. You never have a coefficient in the middle of a statement. That makes no sense. Plus x sine of xy times dy dx plus y times the sine of xy. All equal to this. I can't even put this on one line. So this would be 2xy. So how about 2xy e to the xy squared dy dx? And then finally, plus y squared e to the xy squared. Now I can gather the dy dx terms. I'm going to put them all on the left side. So that means that this term here is going to go on the other side. And this term here, which doesn't have a dy dx, that's going to go on the right side. It looks like, oh, and this one over here too. That's going to go. So these two terms I'm going to throw on the right side. This term I'm going to throw on the left side. And when I do that, I will have my final answer. Well, one step away. So I have 2x cubed y plus x times the sine of xy minus 2xy e to the xy squared, all times dy dx. Those are the three terms that all have dy dx's in them. The right side is going to be this term minus this term minus this term. I think I can get this in here. So the answer, dy dx is the quotient. Okay, this is my denominator. And this is my numerator. Oh boy. Now you remember how much fun you had back in Calc 1. Yeah, that's why you didn't love I just hope I didn't make any mistakes along the way. So let's do a quick check. First times derivative of second, okay. Second times derivative of first, okay. Plus the sign times the derivative of the argument, first derivative, second derivative, first, equals E, and then derivative of the argument first times derivative of second plus second times derivative of first. I mean, I'm not wasting any steps. That's a lot of work. That's way too much work for me. I'd rather be doing something else. You know, there's probably a hockey game on somewhere in the world, but that's our answer. Yikes. So let's do this. I'm going to leave the original problem up there because I won't remember it. I'm going to leave the answer at the bottom, but I'm going to erase everything in between. There's an easier way, but not using Calc 1. Now, I made this statement recently, said everything you've ever considered in Calc 1 can be considered a slice of something three-dimensional, right? I mean, something as simple as a circle, I can think of as being a slice of a circular paraboloid, right? The bullet shape. Everything, no matter how icky it is in 2 dimensions, can come from a function in 3 dimensions. So icky derivatives in 2 dimensions can end up being simple derivatives in 3 dimensions because implicit means I could not isolate the dependent variable. But what if X and Y were both independent variables? Then derivatives might be a lot easier. So I'm going to go what if at you. Let's just say I have Y equals X squared. So I have Y equals F of X. And we said this before, if I rewrite Z as Y minus F of X or F of X minus Y, I've made Z now a function of X and Y. Well, I haven't changed anything. How is it the same thing? Because remember, if I pick Z equals 0, that's just one of my level curves. So if I wanted to do this, think of it as a 3-dimensional thing. So if I have something as simple as a circle, X squared plus Y squared equals R squared. If I said, let's call Z X squared plus Y squared minus R squared, this is a circular paraboloid. In fact, it's a circular paraboloid that starts off exactly R squared units below the XY plane. And where this intersects the XY plane is exactly the circle. I can absolutely, for everything that exists, I can do this. Not that I should, I can. Everything 2-dimensional, I can make it a 3-dimensional slice. So this circle in the XY plane comes from this where I set the Z equal to 0. But I could have set Z equal to a larger number or a smaller number. So with that said, what if I've got something of the form Y equals F of X, and what I want to do is create a 3-dimensional function. So let's do it by, when I throw everything to the same side so that it equals 0, let's let W equal some new function. I'll call it capital F of XY. Not the same thing. Where all I did was take the difference between, I threw everything on the same side so it was all equal to 0. So in the case of my circle, it was X squared plus Y squared minus R squared. That's what I called this guy here. I'm going to use a different letter rather than Z. I'm going to call it W. I don't know why, it's kind of the traditional letter. Now here's what I want to do. I want to differentiate both sides of this with respect to X. It's understood that Y is a function of X, or you could say Y equals Y of X, if that makes it easier. I'm starting with Y being a function of X, just like before. So if I say differentiate both sides with respect to X, then what have I got? Well, because W sees 2 variables. So I'd say the partial of W with respect to X. Oh, and by the way, what is the derivative of W? Doesn't it have to be 0? This is the problem we just did a moment ago. So this would be the partial of F with respect to X times the derivative of X. Of course, that would be 1. Plus the partial of F with respect to Y times the derivative of Y with respect to X. Now, obviously that's a 1. Obviously that's a dy dx. But I'm using the formal notation that we just did. Okay. How about if I rewrite that as that? I like that notation better just because it's easier to write and there's no confusion. Times 1 times dy dx. Okay, why is this even important? Because the left side is 0. My goal was to find dy dx. I have something, y is a function of x. Maybe it's implicitly defined, maybe it's explicitly defined, but y is a function of x. I can always throw everything on the same side and say, let's call that a new function of x and y, and it automatically equals 0. Great. If I get dy dx by itself, won't this read fy dy dx equals negative fx? And that means that dy dx would be the negative of fx over fy. Huh. What do you suppose that means? That means for anything you can possibly write in 2 dimensions that has 2 variables, whether you're writing y as a function of x explicitly, y equals e to the x, or you've got like a circle, you got x's and y's, you can't isolate the y, but you're saying, I'm going to treat y as a function of x because I want the slope of the tangent line. I want a dy dx. So it's either explicit or it's implicit. But if I set up the problem in this way, I'm saying that your derivative you're looking for is just this. I don't think that's going to be very complicated. Let's apply that, how about to this problem right here? That's why I left it up there. I think you're going to like this. I'll leave that there for just a second. So the first thing I need to do, I can't start by taking derivatives. I need to create a function. So if I say, let's take this minus this, or I could say, let's take this minus this, it really doesn't matter. So I'm going to define a function, capital F of xy, and it's going to be x cubed y squared minus the cosine of xy minus e to the xy squared. I have to create a function, okay? The fact that this equals 0, I can say equals 0, it doesn't really matter, because when I differentiate, right? To say the function equals 0 has nothing to do with the derivatives. The derivatives are not 0. No. That'd be like saying every time you have an equation and you set your equation equal to 0, that all derivatives would be 0. No, probably none of them are 0. No. The combination of things is 0, not the individual things. So what is fx? What's the partial with respect to x? Let's do that. Let's see. That would be 3x squared y squared. With respect to x, I'm going to have a sine of xy, but with respect to x, y is the coefficient. Everybody got that one? With respect to x, I'm going to have e to the xy squared, but y squared would be the coefficient. Okay. Now let's do the partial with respect to y. So that's going to be 2x cubed y. With respect to y, this is going to be sine xy, and now I'm going to have an x in front. With respect to y, the derivative of that with respect to y would be 2xy. So now if I do this, then my answer is going to be the negative of this over this, okay? Well, look at that for a moment. Isn't that my denominator right now? Exactly. Yes. If I take the negative of this, that's my numerator exactly. This is the entire problem. You gotta like that. Yeah, implicit differentiation, you're never going to struggle with again. It's actually really, really easy if I think of it as a 3-dimensional problem and I take partial derivatives. So why didn't they show us this in Calc 1? Because you didn't know how to do partial derivatives in Calc 1. In case you're wondering, implicit differentiation was day 5 of Calc 1. We haven't, all we knew how to do at that point was differentiate polynomials and trig functions. We hadn't even gotten to E yet. So yeah, implicit comes really, really early. But the beautiful thing is I rewrite it, I create a new function, I take my partials, which is usually pretty easy, and then I write my answer. Now, you can leave the negative in front, you can distribute the negative into either the numerator or the denominator. If I distribute the negative into the numerator, where is it? That would have changed sign, that changed sign, that changed sign. Yeah, so it didn't matter. It's the same answer. I prefer this way because it's just so much simpler, it's so much shorter, and I'm far less likely to make an error. So let's try another one. All right, let's say that, let's keep it simple. I want to find dy dx. Oops, sorry, that's one. Find dy dx, and we have, how about x squared tan y equals, I don't know, e to the x cubed y squared, something diabolical. It's not possible to solve for either one of the variables, but partial derivatives of something that looks like that's easy. Now, you cannot start by taking derivatives. You actually have to have a function. Right now, I have an equation. Ooh, got to be careful. Taking derivatives of the equation isn't going to be useful. I have to take the derivatives of a function because I have to be able to set it equal to something. So what we do is we first rewrite it. Oh, black pen. So we choose, I'm going to use capital F again because I haven't used that for anything else. It does not matter which way you subtract. It just matters that you have something that is officially equal to 0, because that's how we derived this. Now I'm going to take partial derivatives with respect to x and with respect to y and then write my answer. See, if I try to do partials on here, I will still have an equation, and that's not going to be very useful. The partial with respect to x is 2x tan y minus e to the x cubed y squared times the derivative of the argument with respect to x. So the derivative of this with respect to x would be 3x squared, and then y squared. That's it. There's no product rule because I don't have the product of two functions of the same variable. That's a huge time saver. But if I did it implicitly, yes, I'd have to use product rule all over the place. The partial with respect to y, well, the derivative of the tangent of y is the secant squared of y. The derivative of x cubed y squared with respect to y would be 2y. So that'd be 2x cubed y. Now, finally, I'm going to write my final answer. So dy dx is a negative of. Now, what always throws people is the order. You notice when we did it, the x derivative goes on top, not the y derivative. There's two places where people make mistake. The first one is they forget the negative sign, and that does matter. The second one is they got these things flipped. That's probably a bigger error. So this guy goes on top, 2x tan y minus 3x squared y squared e to the x cubed y squared. This guy goes on bottom, x squared secant squared y minus 2x cubed y. This is a perfectly acceptable answer, or you can multiply this on the top, or you can multiply this on the bottom. You can't multiply top and the bottom. Okay, that would be incorrect. If you multiply top and bottom by -1, then you haven't changed the sign at all. No, you can't do that. So I can leave it here. Now, here's the mistake. Don't write this down. This is the universal mistake I see people do. See that negative? This answer is now 100% wrong. It is not equal. In fact, this isn't even close to the previous answer. This was a difference. Now they're the same sign. Oops. If I'm going to put the negative here, folks, it's got to be that. I would have to distribute the negative. You can't simply bring it up in front of one term. In remedial algebra, distributing of a negative sign is one of the most common errors. Bad distributing of a negative. We only put it in the first term. No, you would have to distribute it to every term if you want to multiply it in. So either leave it in front or multiply it all the way in, either one. This is the shortcut for implicit differentiation, which most of you will love. Now, what if we have more than two variables? Let's do something a little more complicated. All right. And I don't want to make it, well, okay, I want to make it a little bit icky. So what if we said, let's suppose z is a function of x and y. All right, z is a function of x and y. And I want to find, let's say, the partial of z with respect to x in the following quantity. X squared y minus y cubed, oops, sorry, y cubed smearing all over the place. Z equals Z squared. Okay, I cannot isolate any of the variables. But like the original implicit differentiation problem, when I said, let's assume y is actually y of x, this is not a variable z, this is a function z. This z is a function of x and y. Okay, x and y are independent variables, z is a function of x and y. So I want to find this. So what does that mean I have to do? That means I have to differentiate both sides of this with respect to x. Yx, because that's the one on the bottom. Okay, and what I'm looking for are the partial of z with respect to x terms. So y is a coefficient, okay, because I'm differentiating with respect to x. So this would be 2xy. Now z is a function of x and y. Ooh, so I actually have to consider, I'm differentiating with respect to x. So the first times derivative of the second times the derivative of the first would be 0 because y is not a function of x. Okay, so to differentiate the variable y with respect to x is 0 because y is independent, but z is not. So y, so in this case, again, I'm treating y like a coefficient. On the other side, this would be 2z to the first partial of z with respect to x. Now, this is not terrible. This is far from terrible. So I'm going to send this term over, and I'm going to have 2xy equals 2z plus y partial of z with respect to x. And that would imply that the partial of z with respect to x, if I did this correctly, would be 2xy over 2z plus y. Okay, if I did this correctly. Now, could I use the trick we did before? In other words, could I use the thing where we took the partials and just took the quotient? Well, let's see what would happen if we did. Let's create a new variable, call it g. G of x, y, z. Let's get everything on the same side. So how about x squared y minus yz minus z squared? And of course, then this would equal 0. Now let's find, because I want dz dx, let's find g of z and let's find g of x. Okay, g of z, negative y, negative 2z. Okay, g of x, or I should say g of x, partial of g with respect to x. Sorry, bad on my part. 2xy, and there's nothing here. So here's the question. Is the partial of z with respect to x going to simply equal the negative of gx over gz? Does it work like it did before? Well, let's write that down. That's the negative of 2xy negative y minus 2z. Well, I definitely want to put that negative on the bottom. And if I put it on the bottom, then I'll get 2z plus y. Right? Celebration, rejoicing in the streets. This works no matter how many variables you have. Oh, so if I have multiple variables and I need a single derivative, get everything on one side, take the appropriate partials, you're done. Piece of cake. Yeah. I mean, I love these kind of tricks because they are such tremendous time savers. And there was no part of this that was difficult. All right. So we're done with the chain rule part. Now we're going to go to a very important interpretation of derivatives in 3D. All right. So we know how to do a partial derivative. A partial derivative is basically you hold one of the variables as if it's a constant. So you're looking in that direction or you're looking in that direction. What if I want to look in that direction at an angle? So here's my favorite analogy to use. All right. If you've ever been hiking a Cowles Mountain, okay, raise your hand. I can't see you. All right. I hope most of you have gotten to hike Cowles Mountain. It's a lot of fun. So at any particular point, I'm on Cowles Mountain. Any particular point, if you said, how steep is the climb? Well, it depends. In this direction is really steep. In this direction, it's not quite as steep. In this direction, it's not very steep. In this direction, I'm actually going completely sideways. In this direction, I'm starting to go downhill. In this direction, it's a really steep downhill. So if you said, how steep is it? I have a 360-degree view, and in every single direction that I turn, I'm going to have a completely different steepness if I traveled on a line, I mean. So if you said, how steep is it? You'd have to also say, in which direction? Because the steepness due east is going to be completely unrelated to the steepness due west, and so on and so on. Oh, so when we're asking for steepness, steepness is a two-dimensional thing. Slope is two-dimensional only. It makes no sense to say, what is the slope in 3 dimensions? What are you taking the quotient of? So if you said, well, I'm going to take my z change divided by what? Your x change or your y change? Or is it something different? So this brings the concept of what's called a directional derivative, which quite simply means a derivative in a particular direction. So if I've got a surface, I'll do my best here. One of my favorite surfaces to use, of course, I like the circular paraboloid because it's easy to interpret, it's easy to draw. Okay, I got this guy right here. And let's use z or f of x, y, doesn't matter. All right, so this thing is going this way, you know, kind of looks like a inverted bloomin' onion, you know, over at Outback or something. So at every point on the XY plane, okay, now pick a point on the surface. There's an infinite number of points on the surface. So maybe you're scaling the surface. You're a climber, right? You're one of those rock climbers and you're scaling the surface. So you're probably somewhat upside down. And if I said, how steep is it? Well, doesn't it depend on what direction? Because if you're moving along the y-axis, you're still going up. But if you're moving along the negative y-axis, you're going down. If you're moving, and you can have just the right direction where you're going completely sideways. So once again, your direction is everything. Okay, so what we started by doing with partial derivatives is we said, what's the derivative only in the x direction? Piece of cake, that's partial with respect to x. Only in the y, partial with respect to y. But what if I want a derivative at some other angle? On the xy plane, what if I wanted, you know, a 45-degree angle? How do I ask that question? Well, it's actually not that different. Before, what we did was we said our direction was along an axis, but really your direction, the direction must be a unit vector in the XY plane. See, because even if I'm at Cowles Mountain, doesn't matter if I'm pointing uphill, when we talk direction, north, south, east, west, that's on level surface, sea level, you know, that I'm on the ground. So if I said, okay, go in this direction, okay, now I'm going to start my climb. But if I go in this direction, maybe now I'm going downhill. So the direction is always a two-dimensional thing. Once I pick my direction, and this is what we did when we talked about level curves. Once I pick my direction, now imagine that big old saw is going to come and slice the earth. I've picked this direction, so now a big saw is going to slice the earth, and what I'm going to see is a curve. I'm going to, directly in front of me, I see a curve. And if I said, what is the slope of the tangent line where I'm standing of that curve, that makes perfect sense because that curve is completely two-dimensional. So the curve could be this way, the curve could be this way. I'm going to do a slice, creating a two-dimensional cross-section, and then ask, what's the slope of the tangent line? Now that sounds really complicated, but actually it isn't, because it's either going to be the partial with respect to x if I'm along the x-axis, the partial with respect to y if I'm on the y-axis, or a linear combination of them if I'm somewhere in between. Okay, so what's the linear combination? The unit vector in the xy plane. So what we're going to do is work with partial derivatives. So now I'm going to define something, define a new symbol. All right. Everybody here has seen cars, I hope. And if you haven't, you need to talk to your parents because they probably didn't do a very good job, you know, because you're that right age. In cars, you remember Lightning McQueen's best friend, who was the pickup truck. Anybody remember his name? Come on, y'all remember his name.
Mater.
Mater. And how did Mater define his name? It's Mater without the You guys didn't realize it, but this was all about what we're doing today. That whole movie is about directional derivatives and stuff like that. You don't realize just how much of your movie stuff, shows up in the calculus. Yeah, he's talking about what we're doing today. We're going to define a new symbol. Okay, you all know what this is. What's this symbol? It's the Greek letter delta. Okay. I'm introducing a new symbol to you today. It's an upside down delta. And its definition is delta. Yep. It's exactly, that's what Mater was trying to make reference to, but most 4-year-olds aren't really good at three-dimensional differential calculus. So he had to kind of dumb it down. Yeah. This is called the Dell operator. It is delta without the t. I'm pretty sure that's what Mater was making reference to. I mean, I could be wrong. This is called the Dell operator. You can just call it DEL. Okay. You don't have to say delta and then subtract the t. Just don't put the t in. The Dell operator, it's an operator. It's not a quantity. It doesn't equal anything. In Calc 1, we learn this. This is called the differential operator in Calc 1. It means whatever follows it, I'm going to take the derivative with respect to x. So I apply it to things. Maybe I apply it to this. Maybe I apply it to this. But I apply it to things, and then my result would be this. And here my result would be this. D dx doesn't equal anything, although Calc 1 students have a hard time getting past that. It'd be like me saying, here's a square root symbol. It doesn't equal anything. I have to apply it to something. Here's a limit. It doesn't equal anything. I have to apply the limit of something. The Dell operator is an operator that's different. The Dell operator is, we're going to start with the two-dimensional Dell operator. It's a vector of partial derivative operators. You said, what do you mean? I'm going to apply this to a function. So if I said, and by the way, we actually use vector notation. So if I said the Dell operator applied to f of xy, what does that mean? If I'm applying it to f of xy, then it means I'm doing d dx That's how you interpret it. The Dell operator applied to f of xy, therefore, is the partial of f with respect to x, the partial of f with respect to y. That is a vector. The Dell operator is a vector operator. It means I apply it to a function and I create a vector, and you very specifically create a vector of partial derivatives. Okay? So this is huge. This is new, but this is not hard, but it's really, really important. This vector of partial derivatives is called the gradient. Now, many have heard that word before, but it's extremely unlikely you ever heard it used in its proper context. The gradient is the vector of partial derivatives. That's it. It's the only thing it ever means. A lot of people think there's a key on your calculator because I always have fun with this one. When you go to your modes and you have your different angles, the DRG, degree, radian, and anybody know what the GRA is short for? Because that's not a word. I'm just curious. This is something I learned as a kid before calculators, actually. Does anybody know what GRA stands for? It's short for something, just like DEG is short for something.
Gradient?
No, that's a gradient. It's short for grad, GRAD. You guys never use grads, haven't you? And that's not, I don't mean short for graduates. Grad. 90 degrees is a right angle. Pi over 2 radians is a right angle. 100 grads is a right angle. Grads is a unit, an angular unit measure that is archaic and not used because it's not practical. You say, well, wait a minute, in our system, wouldn't 100 make perfect sense? But what are the most common, what do we consider the common angles? The 30, 45, and the 60. Oh, so if I used 100, I'd have the 33 1/3, and I'd have a 66 2/3, which is just not practical. 90 made more sense because I could subdivide it easier. Degrees are an absolutely artificial made up unit out of convenience. We could have used any number for a right angle. 90 just makes a lot of sense because of its fractions come out really nice. 100 would have made more sense, except that the common angles would all then be really nasty numbers. So you're never in your lifetime going to use grads, but that's what it is. And I don't even know why it's on the calculator, because I've never run across a scenario where it's used, but it's there. It's kind of like, I guess, when you're talking about nautical distances, we talk about, this many knots or this many leagues. Knots is a speed, leagues is a distance, but nobody knows what that means unless you're a 200-year-old sailor, I guess. These are words that mean something. They just don't mean a lot to us because we'd rather use, miles or kilometers rather than leagues, that sort of thing. So a gradient is simply a vector. So let's just do a really simple one. All right. So f of xy is x squared y minus 3y cubed. Okay. Let's find this. This is the gradient of f. That's exactly what that means. So the Dell operator applied to f is the gradient. So this should actually be really simple. The partial with respect to x would be 2xy. The partial with respect to y would be x squared minus 9y squared. Now, more often than not, you're not going to find a gradient as a function. You're going to find the gradient evaluated at a specific point. That's really important because when we're talking about things like directional derivatives, I'd say at this point, what's the slope in this direction? You don't want a formula or a function. You want a value. In that direction, the slope is 1/2. You want a number. So the gradient is part of it. The gradient is the derivatives. Okay, so the gradient tells me the slope. Now I need to choose the direction. And I also need to choose the point. You see, whatever this surface looks like, this is the vector of partial derivatives for every ordered pair on the xy plane. Remember, your input are ordered pairs on the xy plane. Your output is the z values on the surface. For every possible input, this is what the gradient is. But if I say a particular place, I would want that particular xy input. And then I also need the direction because there's a 360-degree rotation that I could choose. So what we do is, we'll say at x naught, y naught, that's the point in question. Okay, so I'm on Cowles Mountain. I'm up in the air, that's fine, but I'm up in the air because there's a z. But if I go down to the xy plane beneath my feet, maybe it's down 100 feet, I don't know. There's an ordered pair that when I input into the function that defines Cowles Mountain, that puts me where I am currently. Great. But if I now said, find the gradient vector, that will tell me the partial derivatives in the x direction, and it'll tell me the partials in the y. And if I choose a direction that is somewhere between the x-axis and the y-axis, I will take a linear combination of those two. But what linear combination? A linear combination from a unit vector. Okay, because in the x direction, it would have been 1, 0. In the y direction, it would have been 0, 1. 45 degrees, how about root 2 over 2, comma root 2 over 2? I need a unit vector that describes the direction that I want to turn. So you have this, and you have, let's say, unit vector u. We usually use u, just makes it easier to remember. So then a directional derivative of f of x, y at x naught, y naught is, and the notation we use is big D, little u, f of x naught, y naught. As I said, you're going to do this at a place. This is a scalar. Is the gradient of f of x naught, or I should say evaluated at x naught, y naught. So I have a vector of constants dotted with the unit vector. Major formula, easy to use. So the directional derivative, and that should make perfect sense, because if I'm going in the x direction, then my unit vector is just 1, 0, and all I would get is the partial with respect to x. If I'm going in the y direction, then my unit vector is 0, 1, and therefore all I would get is the partial with respect to y, which is what we started with. Oh, but if I'm going in any other direction, this gives me the linear combination. This much in the x, this much in the y. Why does it have to be a unit vector? Remember how we talked about this? I want you to go in a general that way direction 100 feet. Well, a general that way direction might be 100 miles. It might be infinite. How long that direction isn't what you want. So we made that a unit vector in that direction and then multiplied our unit vector by the 100. Oh, okay. That's how we went 100 units in that direction. It's the same thing. I don't want the length of my direction to affect it. That's why we always make it a unit vector. So let's do an example of this. All right, let's suppose, let's say there are, okay, some of you need to be muted. I can hear a lot of, sounds like chewing noises, in fact. Again, mute yourself, please. Let's say plus 4x cubed y squared. Okay, so let's find du at, let's say, 3 comma negative 1 in the direction of a equals 6 comma 8. Okay, that's enough information. Now this problem should be relatively simple, but there are stages. So the very first thing I'm going to do is find my gradient vector. Okay, so the gradient vector the partial with respect to x the partial with respect to y next, let's evaluate our gradient vector. I don't want to use this in calculation. It's too big. So we'll evaluate this at 3, negative 1. Excuse me. So if x is 3 and y is negative 1, that'd be negative 18. X is 3, y is negative 1, that'd be 108. So that'd be 90. X is 3, y is negative 1. So that would be 27. X is 3, y is negative 1, so that'd be negative 216. So what's that? That'd be negative 189. And I guess, yeah, that's all we need for that piece. Now we need the unit vector. Is that the unit vector? I think not. Oh, I need to create a unit vector. Pretty much never going to be given the unit vector. You're just going to be told in that direction. I could have made that 6 bazillion, 8 bazillion, and I'll still get the same unit vector. Because first thing I'm going to do is find the magnitude of A, which is 6 squared plus 8 squared under the root. 36 plus 64 is 100. Okay, so my unit vector will be 6 over 10 or 3/5. 8 over 10, which is 4/5. So du f of, where was it? 3, negative 1 is the dot product of this and this. So if you want, I'll write it out. Okay, and just use your handy dandy calculator. So I get negative 486 over 5. That's a terminating decimal, so you can certainly calculate that, but more often than not, right? More often than not, this is probably going to be irrational. So more often than not, this answer is probably irrational. So you can leave it as a reduced quotient. So this is directional derivative. It's just not that difficult in general, as long as you can take your partial derivatives, seamlessly like we did. Now, here's a question. I'm on Cowles Mountain, and I'd like to know what is the maximum value of my directional derivative. Now, I am at a particular place, remember. I'm at a particular place. So at the point 3 comma negative 1 on the xy plane, I would shoot up and I would get the z value. So I'm up high somewhere, I think. Well, maybe not. Maybe I'm, yeah, I think f of 3 negative 1 is probably some fairly large z value. So I'm standing there, a point in space. I have 360 degrees I can look. In which direction is it going to be the steepest? For any point on my surface, is there a way to determine what's the steepest direction? Yeah, actually there is. There's always a maximum slope, in other words, or a maximum directional derivative at every single point. Remember, there's an infinite number of directions I could have chose. So let's think of it like this. I kind of like this one. Most textbooks don't have this. They'll tell you a formula, but they don't always show you where it came from. So let's call our unit vector. How about cos theta sine theta? I know that's a unit vector because cos squared plus sine squared is 1. So there's my generic unit vector. So my directional derivative in the direction of u of x naught y naught would be fx x naught y naught, comma, fy x naught y naught. All right, there's my gradient. That's the general at every single point. I'm sorry, dotted with u. Sorry about that. Got to dot that with u first. Okay, so there's my gradient dotted with u. And what does that give me? That gives me fx x naught y naught times the cosine of theta. Okay. If I did this correctly, plus, there we go. Yeah, fy x naught y naught times the sine of theta. All right. That's what I would get no matter what. I'd like to know, when is this the largest it could ever be? When is it the largest it could be? Well, if I said another way of thinking about this, since this is a dot product, can't I also say magnitude of gradient? I'm gonna leave it like this. The magnitude of the gradient times what? Times the length of the unit vector. Times what else? Times the cosine of the angle between them. I'm going to put in words. Because this theta referred to any of the 365 degrees I could have traveled. The magnitude of this is the same no matter where I am, right? I'm standing on that spot in Cowles Mountain and you found the gradient. Great. Now you found the length of the gradient. Great. Now there's an infinite number of directions I could choose. Which one of them is going to give me the largest dot product? Well, times the cosine of the angle between them. When is the cosine maximized? For what angle is the cosine maximized?
0.
0. Every other angle, the cosine is going to be something smaller than 1. The cosine itself is maximized when the angle is 0. So what's the maximum value of a directional derivative? When your unit vector is in the same direction as the gradient. Oh, now the gradient and the unit vector have nothing to do with each other. The gradient is just the vector of partial derivatives. And given a point, remember when we did this earlier, we did this for a particular point, and I got a gradient vector with numbers in it. But if I thought of that as the direction I also want to travel, that will maximize the value of the directional derivative. So if I choose my unit vector to be the unit vector in the direction of the gradient. So if I choose u to be 1 over the length of the gradient, I'm just going to be generic, times the gradient vector. Then when I do the gradient vector dotted with u, like this, isn't a vector dotted with itself the same as the square of its magnitude? Oh my gosh. So first of all, what direction maximizes the value of a directional derivative? A direction that is the same as the gradient. What is the value? What is the maximum value then a directional derivative can be? The magnitude of the gradient. Oh, how nice. That's beautiful. Now, I found that point on my gradients, right? I got a gradient vector and my gradient vector is in this direction. Then if I want the steepest climb, go in this direction. Now, what if I want the minimum value of the directional derivative? I've chosen a general this way direction for my steepest ascent. Anybody want to guess exactly what direction will be my steepest downhill? If this is the steepest uphill where I'm standing, how about if I,
The inverse.
the inverse, what's the inverse of a direction? How about, different word, how about the opposite direction? Everybody got that? If whichever way I'm pointing gives me the steepest uphill, what if I go exactly 180 degrees the other way? It's automatically the steepest downhill. Can we prove that? Yeah. When is this going to be minimized? Oh, remember the cosine of the angle between them? What's the maximum value? 1. What's the minimum value? -1. The maximum value happens when the angle is 0. The minimum value happens when the angle is 180 degrees. That makes perfect sense. So whichever direction I pick to maximize the steepness of my climb, if I go exactly 180 degrees, I'd have the steepest downhill. That's automatic. And that should make perfect sense. If you're on a hill in a car and I'm at the point on the hill where I'm the steepest possible climb, then if I was going in the other direction, wouldn't that be the steepest downhill also? Doesn't the steepest uphill have to be at the same point as the steepest downhill? Yeah, that kind of makes sense. So that's directional derivative. Not hard, but one of the first major applications.